All right, so let's get into chemical shift for proton NMR. Now, it's a little bit more complex than carbon NMR, but again, we're going to break it down into regions. And the first kind of region we're going to look at are hydrogens on sp3 hybridized carbons. Now, again, this works the exact same way as chemical shift does in carbon NMR. So the more stuff there is around a hydrogen, especially if it's electronegative, it's going to push that signal farther downfield. So regular hydrogens, let's just say there's nothing remarkable around, are always going to kind of start at around 1 and then get a little bit higher depending on whether if that hydrogen is on if it's primary, secondary, or tertiary carbon. So a primary carbon would have a lower chemical shift than secondary, and then that would be lower than tertiary. But that usually stays within like 1 to 2 ppms. Notice the scale, before I go on, is a little bit different than the scale of carbon NMR. It typically goes from 0 to, some of them stop at 12. You might see some a little bit higher, like 13 or 14, but it doesn't go into the hundreds like carbon NMR does. All right, then next we kind of get into, well, hydrogen's next to more stuff. So I'll focus here on these two. Okay, so those are allylic and benzylic hydrogens. Okay, remember those terms? We've talked about those. When we have a double bond, the first carbon outside of the double bond is the allylic carbon. So the hydrogen on that we call an allylic hydrogen. And then if you have benzene, the first carbon outside benzene is the benzylic carbon. So the hydrogen on it would be a benzylic hydrogen. And again, it follows the same trends where if it was primary allylic, it'd have a slightly less chemical shift or smaller chemical shift than secondary allylic or tertiary allylic. So you still have to kind of take into that account like that stuff rule. But the way I just kind of memorize it is that allylic and benzylic are going to start between 2 and 3 ppm. So you're going to find it somewhere around there. And that's also very similar to a hydrogen next to a carbonyl. So we typically call these alpha hydrogens because they're on the carbon that's alpha to the carbonyl, that first carbon over. And like allylic, they kind of go anywhere between 2 and 3 parts per million. Now, if the hydrogen is next to something really highly electronegative, then you're going to see it start to shift farther downfield. So this range here starts at like 3 and just keeps on going up depending on how electronegative the atom is. And these are hydrogens next to some highly electronegative atom, whether that's an oxygen, a nitrogen, or a halogen. It will push it farther downfield. And if there's more than one, then it's going to go even farther, like starting to go into the 4 and 5 region. So still following that same trend. Now, hydrogens on highly electronegative atoms, like oxygen or nitrogen, we have those up here at the top. They're kind of weird because they can have a chemical shift anywhere from like 1 to 6. And the reason for that is it depends on how much hydrogen bonding it's doing when you take the NMR spectra of that compound. So you could literally take it one day and that proton would be in one position, and then maybe you put it in the fridge, take it out, and um, take the NMR again, and it might be in a different spot because it's not hydrogen bonding to the same degree. So it's just one of those weird things that those typically appear um, in a variety of regions on NMR. And then kind of the last weird one, we saw this with carbon NMR as well, are terminal alkynes. So these are terminal alkyne hydrogens. So alkyne carbons were in a weird spot on carbon NMR, and alkyne hydrogens are in a weird spot. And just kind of memorize it as somewhere between 2 and 3. Now, again, you might look at this and say, well, how am I supposed to know when I got almost every single thing here overlapping what kind of hydrogen it is? Well, you'll have a lot more information. You'll have at least a chemical formula and maybe an IR. IRs can help you with the functional groups. And so in a little bit, I'll go through actual problems of how we can use the proton NMR and how we use it to interpret the structure of a compound. Then we're going to kind of go into our double bond region. So these are hydrogens on sp2 carbons. So these right here. So these are your typical vinylic hydrogens. Vinylic stands for a hydrogen on a double bond. So kind of memorize those somewhere between 4 and 6. And then 6 to 8, you're going to have aromatic hydrogens or hydrogens on benzene. Outside of that, then we get into like two very specific functional groups. These are the only types of hydrogens you'll see with this high of a chemical shift, and that's carboxylic acid hydrogens and aldehyde hydrogens. Those two types of hydrogens have the highest chemical shift of all functional groups. All right, so there's a little bit of memorizing here, and there's a little bit of generalizing. But if you kind of have the foundation and then you realize, then you like remember the rule. It's not a rule, but kind of the terminology. The more stuff there is around a hydrogen, the farther downfield it's going to go. So let's look at some examples. And let's start here by looking at toluene. I'm going to draw the structure and kind of ignore the NMR for right now. I'll just do that so you're not looking at it. And I'm going to draw all the hydrogens in. And let's do some predictions. Okay, well, first of all, how many signals should we see? Well, the CH3 is going to be unique. Those 3 hydrogens are equivalent to each other. And then these 2 hydrogens are related by symmetry. These 2 hydrogens are related by symmetry. And then this hydrogen is on its own. So we should see 4 signals. Let's do some predicting about where we would see them. Okay, well, a hydrogen is benzylic. So we might see it somewhere between 2 and 3. And then hydrogens B through D are aromatic. So we would probably see those somewhere, let's just kind of average it out and say somewhere around 7. Maybe a little more, maybe a little less, just depends on the compound. So if we go to now look at our spectra, we see that if we look upfield, there is a signal between 2 and 3. There's our A hydrogens. What is this int equals 3 thing? This is our integration. Remember, integration tells us the relative number of hydrogens. Here, it just flat out tells us that that signal represents 3 hydrogens. And if we look at what a CH3 is, it has 3 hydrogens on it. Now, we have predicted that B, C, and D B, C, and D are unique. So we should see like 3 signals in that aromatic region. Why am I only seeing 1? Well, the reason is that all 3 of those are so close in chemical shift, they're kind of overlapping. And so you might have, 1 signal look like this, and then you might have another signal kind of look like this, and then yet a third one maybe look like this. And it's just all one big mess. But It's where we predicted. We predicted it should be somewhere around 7. So this clump of signals represents hydrogens B, C, and D. But notice that by taking the integration of that huge clump of signals, it comes out to a value of 5. Well, how many B, C, and D hydrogens are there? Well, there's a total of 5 of them. 2 B's, 2 C's, and 1 D. All right, let's look at another example. So here is para-dietert-butylbenzene. And let's, again, before we look at the spectra, let's do some predicting. First of all, how many signals will we see? Well, all 9 of these guys here are equivalent to each other. I'm not going to draw all 9 of them out, but notice that they're all attached to this same quaternary carbon. And we'd say the same thing for the ones on the bottom. All 9 of them are attached to the quaternary carbon. And because this is related by symmetry, these are also A hydrogens. Now I'm going to draw in these 4 on benzene. And do you see any equivalent or unique hydrogens there? So let's just start off by calling this B. If you look at this, that hydrogen is also in the same exact environment. It's related by symmetry. This one is in the exact same environment, and this one as well. So all 4 of those are equivalent to each other. And again, let's do some predicting. So where would we see the A hydrogens at? Well, the A hydrogens are not benzylic. They're another carbon outwards, so it's going to be farther upfield than like 2. We can kind of look at them as normal, just hydrogens on primary carbons. So let's just say somewhere between maybe 1 and 1.5. And then the B hydrogens are aromatic. So somewhere between 6 and 8. Let's average that out to say somewhere around 7. And if I go to the NMR, notice at around 1 and close to 1.5, like where I predicted, there's a signal there. Those are my A hydrogens. And then the B hydrogens, I predicted somewhere around 7. That's where they are, the aromatic ones. Now let's look at the integration values here. So the integration values are 9 A hydrogens, 2 B hydrogens. But if I add them all up, that's not what it is in reality. How many A hydrogens do I have? I have 18 A hydrogens. And how many B hydrogens do I have? I have 4 of them. But wait a second, 18, a ratio of 18 to 4 can also be expressed as 9 to 2. So what these integration values are representing is a relative ratio of the actual number of hydrogens. So be aware that sometimes the integration values that you're given are not the exact number of hydrogens. It's meant to be taken as a ratio. All right, let's look at one more example. We'll do, again, some predictions, and then we'll move on. So here's the structure of methyl acetate. Let's first predict how many signals we should see. So I'll start over here. I'll draw in these 3 hydrogens. That's a CH3. This one's over here is a CH3, so it's got to be equivalent, right? They're both CH3s. Hopefully you're yelling at your screen right now and saying, no, they're not equivalent, because A hydrogens are next to a carbonyl, and these hydrogens are next to a singly bonded oxygen, different chemical environments. Now let's do some predicting of where we would see these. So A hydrogens, those are alpha hydrogens, alpha to a carbonyl. So those are probably going to be somewhere between 2 and 3. And the hydrogens next to an oxygen, those started around 4. Oxygen's a pretty electronegative atom. Let's kind of say somewhere between 3 and 4. So when we go back to our spectra now, we have two signals. There's a signal around somewhere between 2 and 3. That's our A hydrogen. And then there's that signal between 3 and 4 for our B hydrogens. Again, let's look at the integration here. The integration says A is 1 and B is 1. But we know that's not the case in the formula for methyl acetate. What this is saying is that the ratio of A to B should be 1 to 1. And in fact, they are. There's 3 A hydrogens and 3 B hydrogens. Yet our integration just kind of gives us that ratio in the lowest terms. Now, in one of our final, or I should say the final video of this series, we're going to be looking at those weird, this concept of splitting that occurs in proton NMR, where these signals don't necessarily always show up as a single peak, but they get split into multiple ones. We'll talk about what that means and why this happens.